There is something deeply strange about the fact that you exist at all. Not strange in the polite philosophical way people mean when they say it at dinner parties to sound interesting. Strange in the way that should genuinely unsettle you if you let it. Strange in the way that the smartest minds of the last century found themselves unable to sleep over it, not because they lacked intelligence, but because the more intelligence they brought to bear on the question, the worse the problem became. Here is what we know. The universe is not eternal. It had a beginning. There was a moment, not a long time ago in the comfortable sense, not the way ancient Rome feels distant, but a moment of absolute, total, non-negotiable origin, before which there was nothing. No space, no time, no matter, no darkness, because darkness is something, and there was not even that. And then there was everything. In an instant so brief it makes the entire lifespan of every star that has ever burned look like an afternoon. The whole of physical reality came into existence from a state that our mathematics cannot describe and our intuitions cannot reach. That should bother you. It bothers physicists. It has bothered them for a century. But here is the part nobody quite prepares you for. Long before the physicists arrived at this conclusion, long before the telescopes, the spectral analysis, the cosmic microwave background radiation, the mathematical proofs, an ancient religious text made exactly this claim. The Bible, written across centuries ending roughly 2,000 years ago, opens with a declaration so specific that modern cosmologists have found themselves in the uncomfortable position of confirming it. In the beginning, it says, not in the eternal past, not after a long period of cosmic stability, in the beginning, as in there was one, as in something started. For most of the 20th century, the scientific consensus ran in the opposite direction. Not because scientists were hostile to the idea of a beginning, though some were, and we will get to that, but because the mathematics of a universe with a definable starting point created problems that seemed almost too large to solve. An eternal, steady-state universe was, for a long time, simply easier. Philosophically tidier. It didn't require you to answer the question that a universe with a beginning immediately forces you to confront, which is, what caused it, and what came before, and why is there something rather than nothing? These are not small questions. These are the questions that made some of the greatest physicists of the modern era choose the wrong answer rather than face them. The story of how science spent roughly 100 years resisting, revising, debating, and ultimately arriving at what a shepherd writing in the ancient Near East apparently already knew is one of the most extraordinary intellectual journeys in human history. It involves a Belgian priest doing astrophysics in a monastery. It involves Albert Einstein inserting a fudge factor into his own equations because he didn't like what they were telling him, then calling it the greatest blunder of his career. It involves a man named Edwin Hubble standing at the eyepiece of the largest telescope on Earth and watching galaxies race away from him in every direction. It involves a pair of radio engineers who stumbled onto the echo of creation itself while trying to figure out why their antenna kept picking up static that wouldn't go away. And woven through all of it, never loudly, never with particular agenda, but persistently, is the question that nobody in science particularly wanted to discuss in polite company. If the universe had a beginning, if the evidence is now overwhelming and the consensus essentially total, then what does that mean for the oldest claim in Western civilization's most widely read text? Not a theological question exactly, a scientific one. Because the Bible didn't just say the universe began, it said the universe was created. And it turns out those are two very different statements, and only one of them is something science can currently test. We are going to follow the science. All of it. The part that makes believers uncomfortable, the part that makes atheists uncomfortable, and the very long middle section that should make everyone deeply, productively unsure of what they think they know, because the honest answer, at the end of a century of extraordinary cosmological science, is not triumphant in either direction. It is something stranger and more interesting than that. It always is. To find the moment when this question stopped being theology and started becoming science, you have to go to Belgium in the 1920s, to a man who had no business being as interesting as he was. Georges Lemaitre was a Catholic priest. He was also simultaneously one of the most gifted theoretical physicists in Europe. This combination struck many of his contemporaries as either charming or suspicious, depending on their dispositions, but Lemaitre himself seemed unbothered by the tension. He wore his clerical collar to physics conferences. He said mass in the mornings. In the afternoons, he solved Einstein's field equations. He appeared to experience no contradiction between these activities, which was either a sign of profound intellectual integration or a level of compartmentalization so advanced it bordered on the superhuman. In 1927, Lemaitre published a paper in a relatively obscure Belgian scientific journal. It was written in French, which limited its immediate audience, and it appeared in a publication that most of the major figures in European physics were not in the habit of reading. The paper contained something remarkable. Working independently from the observational work being done in California at the time, Lemaitre had derived from Einstein's general relativity equations a conclusion that Einstein himself had gone to considerable lengths to avoid. The universe, Lemaitre's mathematics showed, was not static, it was expanding. And if it was expanding, then running that expansion backward in time led to an unavoidable conclusion. There had been a moment of origin, a point of maximum compression from which everything had emerged. Einstein, when he eventually encountered Lemaitre's work, was not pleased. He told Lemaitre, in what has become one of the more famous dismissals in scientific history, that his mathematics were correct but his physics were abominable. This is an interesting thing to say to someone whose physics were, as it turned out, entirely right. But Einstein's resistance was not purely ego. He had reasons, and they are worth understanding because they illuminate just how psychologically difficult it was for even the greatest scientific mind of the century to accept what the equations were saying. When Einstein had first applied his general relativity equations to the universe as a whole, back in 1917, the equations had refused to produce a static universe. They kept insisting on a universe that was either expanding or contracting. Einstein found this unacceptable. The prevailing scientific view at the time was that the universe was eternal and unchanging, what physicists called a steady-state model, and Einstein wanted his equations to support that view. So he did something that scientists are not supposed to do. He invented a term. He added what he called the cosmological constant, a kind of mathematical counterweight, to his equations, specifically to make them produce the result he expected, rather than the result they were naturally generating. He essentially inserted a fudge factor into the most elegant equations in the history of physics because he didn't like their answer. He would later call this the greatest blunder of his career. But that regret came later. In the late 1910s and through the 1920s, Einstein's cosmological constant stood like a wall between the mathematics of general relativity and their obvious implication. The universe had a beginning. The equations said so, and some very brilliant people spent a great deal of effort not noticing. While Lemaitre was doing his theoretical work in Belgium, something was happening in the mountains above Los Angeles that would eventually make the theoretical argument irrelevant. The Mount Wilson Observatory, sitting at nearly 6,000 feet in the San Gabriel Mountains, had been completed in 1917 and housed what was then the largest telescope on Earth, the Hooker telescope, with its 100-inch mirror. It was here, in the early hours of October 6, 1923, that an astronomer named Edwin Hubble made an observation that would, within a few years, change our understanding of the universe more fundamentally than anything since Copernicus. Hubble was examining a photographic plate of the Andromeda Nebula, a fuzzy patch of light that astronomers had debated the nature of for decades. Some believed it was a gas cloud within our own galaxy. Others had long suspected it might be something else entirely. On that October night, Hubble identified a specific type of star in the nebula, a Cepheid variable, whose brightness fluctuated in a predictable pattern that allowed astronomers to calculate its actual distance. When Hubble did the calculation, the number that came back was staggering. Andromeda was not inside our galaxy. It was roughly 900,000 light-years away, outside the Milky Way entirely, a separate galaxy of hundreds of billions of stars. The universe was not the size anyone had thought. It was almost incomprehensibly larger. But that was only the first half of what Hubble would discover. Over the following years, working with his colleague Milton Humason, Hubble began measuring the light from these distant galaxies and noticed something in the spectra that should not have been there. The light from almost every galaxy he examined was shifted toward the red end of the spectrum. This redshift, as it was known, indicated that the galaxies were moving away from Earth, not just a few of them, all of them, in every direction. And the further away a galaxy was, the faster it appeared to be receding. In 1929, Hubble published this relationship, now known as Hubble's law, and the implication was immediate and inescapable to anyone willing to look at it directly. If every galaxy is moving away from every other galaxy, then in the past they were all closer together. Further back still, they were packed together. And at some definite point in the finite past, they were all in the same place. The universe had not always been as it is. It had been smaller. And before that, smaller still. And before that, there was a moment of origin. When Einstein saw Hubble's observational data in 1931, he visited the Mount Wilson Observatory in person. He stood at the Hooker telescope and examined the evidence. And then, with a characteristic economy that made the moment even more significant, he declared that the cosmological constant, his great blunder, his deliberate resistance to what his own equations had been telling him for over a decade, was to be abandoned. The universe was expanding. It had begun. The mathematics had been right all along. Lemaitre, meanwhile, had gone further. In 1931, the same year Einstein made his pilgrimage to Mount Wilson, the Belgian priest published a short but extraordinary paper in the journal Nature, suggesting that the expansion of the universe, and traced backward to its logical conclusion, implied what he called a hypothesis of the primeval atom. All the matter and energy in the cosmos had once been compressed into a single, extraordinarily dense point, and the universe had begun with what he described as the fireworks of that primeval atom's disintegration. It was, in outline, the Big Bang theory, proposed by a Catholic priest, derived from mathematics that a Jewish physicist had initially tried to suppress. Published in the same decade, that radio engineers in New Jersey would accidentally discover its echo still ringing through the universe. The history of cosmology has never been particularly tidy. Before we go any further into the science, we need to stop and actually reckon with the size of what we are talking about. Because one of the quiet problems with cosmology as a subject is that the numbers involved are so large they stop meaning anything almost immediately. 1 billion light-years, 1 trillion stars. These phrases pass through the mind like water through a sieve, acknowledged, then gone. So let's try to do this properly. The observable universe, the portion of the cosmos we can actually detect from Earth, limited by the distance light has had time to travel since the beginning, is approximately 93 billion light-years across. A light-year is the distance light travels in a single year, moving at 186,000 miles per second. If you drove a car at highway speed, without stopping, without sleeping, without any of the biological inconveniences that make long drives unpleasant, it would take you roughly 70,000 years to reach the nearest star beyond our Sun. That star is 4.24 light-years away. The observable universe is 93 billion light-years across. The arithmetic of that comparison is not something the human brain handles gracefully, and there is no shame in that. Let's try another approach. Our own galaxy, the Milky Way, it contains somewhere between 100 and 400 billion stars. If you tried to count them at a rate of 1 per second without pause, it would take you between 3,000 and 12,000 years to finish. The Milky Way is one galaxy. The observable universe contains an estimated 2 trillion galaxies. 2 trillion. When astronomers revised that estimate upward in 2016, it had previously been around 200 billion. The announcement passed through the news cycle in about 48 hours and then disappeared. We collectively processed the information that the universe contained 10 times more galaxies than we had thought, and then moved on to other things. This seems in retrospect like an underreaction. Now here is the part that matters for our story. All of that, every star in every one of those 2 trillion galaxies, every planet, every gas cloud, every black hole, every particle of dust drifting in the void between galaxies, all of it emerged from a single point of origin, not a large point, not a region of space. A singularity in the mathematical sense, a point of infinite density and zero volume at which the normal rules of physics as we understand them cease to apply. Everything that exists was once compressed into something with no size at all. If that sentence doesn't make you uncomfortable, you haven't fully absorbed it yet. Think of it this way. Take the Sun. The Sun is so large that approximately 1.3 million Earths could fit inside it. Our Sun is, by stellar standards, fairly average in size. There are stars in our galaxy that make the Sun look like a marble next to a hot air balloon. Now take every star in the observable universe, every single one of those estimated 200 sextillion stars, that's a 2 followed by 23 zeros, and compress them, along with all the matter and energy that exists in any form, into a space smaller than a single proton. A proton is roughly a millionth of a billionth of a meter across. You cannot see it. You cannot feel it. The best microscopes ever built cannot resolve it visually. And the entire universe, all of it, was once denser than that. This is what the Big Bang Theory actually says. Are not an explosion in space. That is the popular misconception, and it is worth correcting. There was no pre-existing space for the explosion to happen in. Space itself did not exist before the beginning. Time itself did not exist before the beginning. The Big Bang was not an event that occurred within the universe. It was the event from which the universe, including space, including time, emerged. Asking what existed before the Big Bang is, in the strict physical sense, like asking what is north of the North Pole. The question assumes a framework that doesn't apply. Our own planet, to bring the scale back down for a moment, is about 4.5 billion years old. The universe is approximately 13.8 billion years old. So Earth has existed for roughly a third of the universe's total lifespan. The Sun won't burn out for another 5 billion years or so, which means that from the moment of creation to the moment our solar system goes dark, the Sun and Earth together will have occupied only a small fraction of whatever the universe's total story turns out to be. We are not at the beginning of things. We are not near the end. We are somewhere in the middle of a story whose final chapters have not been written and whose first page is, in the most literal physical sense, inaccessible to us. That inaccessibility is not a minor technical problem. It is the central challenge of the entire field. The moment of the Big Bang itself, and the first tiny fractions of a second after it exist behind what physicists call the Planck wall, a barrier beyond which our current mathematics and physics simply break down. We cannot see past it, calculate past it, or theoretically model what lies behind it with any tool currently available to science. Everything we know about the beginning of the universe is inferred from what came after. The universe we observe today is, in a sense, the only evidence we have for the event that created it. Working out how the universe began from the universe as it currently exists is a bit like trying to reconstruct the recipe for a cake by eating a single slice, decades after it was baked. You can learn a great deal, but there will always be things you cannot reach, so let's actually do the science. Because the history is remarkable, but the physics underneath it is where things get genuinely strange. When Hubble confirmed that galaxies were rushing away from each other in every direction, the natural question was not just whether the universe had a beginning, but what that beginning actually looked like. And here is where most people's mental image goes wrong. When we say the universe began in a hot, dense state and expanded from there, the brain automatically reaches for a familiar picture. A bomb going off, a fireball expanding outward through empty space, debris flying in all directions from a central point. That picture is wrong in almost every important detail, and understanding why it's wrong is actually the key to understanding what the Big Bang really was. There was no empty space for the universe to expand into. Space itself was created in the expansion. There was no central point from which everything flew outward. Every point in the universe is, in a meaningful sense, the center. If you were standing in a galaxy 1 billion light years from here, you would see every other galaxy racing away from you, just as we see them racing away from us. This is because it is not that galaxies are moving through space. It is that space itself is stretching. The distance between any 2 points in the universe is growing, not because those points are traveling, but because the fabric that contains them is expanding. An analogy that gets this across better than most. Imagine dots drawn on the surface of a balloon. As you inflate the balloon, every dot moves away from every other dot. No dot is at the center of the expansion. Every dot experiences the same thing. That is closer to what is actually happening to the universe, except that the balloon surface has 2 dimensions and the universe has 3, which is where the analogy breaks down and where your head starts to hurt if you think too hard about it. Now, if you run this expansion backward, take the balloon and deflate it, everything gets closer together. The universe gets denser, hotter. The matter and energy that are currently spread across 93 billion light-years of space were once compressed into an unimaginably small volume, and the temperature of that compressed state was correspondingly unimaginable. At 1 second after the Big Bang, the universe was approximately 10 billion degrees Celsius. To put that in perspective, the center of our Sun, where nuclear fusion is happening continuously, is about 15 million degrees. 1 second after the Big Bang, the universe was roughly 1,000 times hotter than the core of the Sun, and 1 second is an eternity compared to what came before it. In the first fraction of a second, and we are talking about intervals so small they require scientific notation just to write down, the universe went through a sequence of transformations that determined essentially everything about the physical reality we inhabit today. At 1/10,000th of a second after the beginning, the universe was so hot and dense that even protons and neutrons couldn't hold together. Matter existed not as atoms, not even as the particles that make up atoms, but as a seething soup of quarks and gluons, the fundamental constituents of matter at its most basic level. This state is called a quark-gluon plasma, and we have actually recreated it briefly in particle accelerators like the Large Hadron Collider at CERN. When physicists smash protons together at nearly the speed of light, they generate temperatures high enough to dissolve protons back into their constituent quarks just for an instant. They are essentially recreating a tiny pocket of conditions that existed in the entire universe a fraction of a second after it began. The fact that we can do this at all says something extraordinary about the coherence of physics across 13.8 billion years of cosmic history. As the universe expanded, it cooled. And as it cooled, things became possible that had not been possible before. At around 1/10,000th of a second after the Big Bang, the temperature dropped enough for quarks to bind together into protons and neutrons, the building blocks of atomic nuclei. This process is called hadronization, and it represents the first moment in cosmic history when anything resembling ordinary matter existed. But the universe at this stage was still so hot that no atom could form. If a proton and an electron happened to come together, the ambient radiation was energetic enough to immediately blast them apart again. The universe was an opaque plasma, a fog of charged particles so dense that light could not travel through it. If you had eyes that could function in those conditions, which you absolutely could not, you would see nothing. Not darkness, just an impenetrable wall of glowing energy in every direction. This state persisted for a surprisingly long time, roughly 380,000 years. That sounds like a brief interlude on cosmic timescales, but it is longer than modern humans have been anatomically modern. For 380,000 years after the Big Bang, the universe remained this opaque plasma, gradually cooling, slowly thinning. And then something happened that cosmologists call recombination, though as with many scientific names, the word is slightly misleading since the electrons and protons had never been combined before. When the temperature dropped to roughly 3,000 degrees Celsius, electrons lost enough energy to be captured by protons and stay captured. Hydrogen atoms formed, and the moment hydrogen atoms formed, the universe became transparent. The light that had been trapped in the plasma, the radiation that had been bouncing around for 380,000 years, unable to travel freely, was suddenly released. It flooded outward in every direction simultaneously. And here is the thing about that light that should genuinely astonish you. It is still travelling. It has been travelling for 13.8 billion years, and it is still out there. You shifted by the expansion of the universe from visible light down to microwave radiation, now washing over the Earth from every direction in the sky. We can detect it with the right instruments. We have been detecting it since 1965. That is what Arno Penzias and Robert Wilson, two radio engineers working for Bell Telephone Laboratories in Holmdel, New Jersey, accidentally stumbled onto while troubleshooting a horn antenna they were using for satellite communication work. The story of how the cosmic microwave background radiation was discovered is one of the great accidental discoveries in scientific history, and it deserves a moment. Penzias and Wilson were not looking for the echo of the Big Bang. They were trying to remove a persistent background noise from their antenna, a low-level hiss that was present regardless of where they pointed the instrument. They checked everything. They recalibrated. They looked for sources of local interference. They famously evicted a pair of pigeons that had nested inside the antenna and left what Penzias diplomatically called a white dielectric material coating the interior surfaces, which is to say, pigeon droppings. They cleaned it out. The hiss remained. It came equally from every direction in the sky, at every time of day, at every point in the year. It was not coming from a local source. It was not an instrument error. The universe itself was humming, at a temperature corresponding to about 2.7 degrees above absolute zero, and this antenna was hearing it. Meanwhile, just 37 miles away at Princeton University, a team led by Robert Dick had independently predicted that exactly this kind of background radiation should exist, and they were in the process of building equipment to search for it. When Penzias called Dickey to describe what he and Wilson had found, Dicker reportedly turned to his colleagues and said simply, "Boys, we've been scooped." Penzias and Wilson won the Nobel Prize in Physics in 1978 for their discovery. Dicker did not, which is one of those small injustices that science occasionally produces and nobody quite knows how to correct. The cosmic microwave background, the CMB as it's usually called, is now one of the most precisely measured phenomena in physics. Satellite missions including NASA's COBE mission in 1989, the WMAP mission in 2001, and the European Space Agency's Planck satellite in 2009 have mapped it across the entire sky with extraordinary resolution. What they found is a near-perfect uniform glow at 2.725 degrees Kelvin, with tiny temperature fluctuations of roughly 1 part in 100,000. Those fluctuations are not noise. They are the fossil record of slight variations in the density of the early universe. Quantum fluctuations in the primordial plasma that over billions of years would be amplified by gravity into the large-scale structure of the cosmos, the filaments and voids and galaxy clusters that make up the universe as we observe it today. The CMB is, in this sense, not just evidence of the Big Bang. It is the blueprint of everything that came after. In those tiny temperature variations, the entire fate of the observable universe was already sketched out, 380,000 years after the beginning. But there is a problem with the standard picture, and it took a physicist named Alan Guth to identify it in 1979 while doing calculations at Stanford that kept producing a number he initially thought was a mistake. The problem is called the horizon problem. If you measure the CMB temperature in one direction of the sky and then measure it in the precisely opposite direction, you get the same temperature to extraordinary precision. This seems unremarkable until you think about what it implies. The two regions of sky you are measuring are so far apart that, given the expansion history of the universe, they could never have been in contact with each other. Light, the fastest thing in the universe, has not had time since the beginning of the universe to travel from one to the other. So how do they know to be the same temperature? Temperature equalization requires thermal contact. If you put a hot object next to a cold one, they reach the same temperature because heat flows between them. But these two regions of the universe have never been able to exchange any information at all. They should have no reason to be the same temperature. And yet they are, to within 1 part in 100,000. Guth's solution was inflation. The idea that in the first unimaginably brief fraction of a second after the Big Bang, the universe underwent a period of exponential expansion so rapid that it makes the subsequent 13.8 billion years of expansion look leisurely. During inflation, the universe is thought to have expanded by a factor of at least 10 to the power of 26, that is, a 1 followed by 26 zeros, in something like 10 to the power of minus 32 seconds. During this period, regions that were initially in close contact and therefore at the same temperature were flung apart faster than light. This is not a violation of relativity, by the way. Nothing moved through space faster than light. Space itself expanded faster than light, which is allowed. The regions that are now on opposite sides of our observable universe were once close enough to equilibrate. Inflation flung them apart, and that is why the CMB is so uniform. Inflation also explains the large-scale structure of the universe in a way that the basic Big Bang model without inflation cannot. During inflation, quantum-scale fluctuations, the random fuzziness that is baked into nature at the smallest scales by the rules of quantum mechanics, were stretched to cosmic proportions. The seeds of every galaxy, every cluster, every vast cosmic filament that spans hundreds of millions of light years were planted in the first fraction of a second of the universe's existence, amplified from quantum noise to macroscopic density variations by the violent stretching of inflation. The universe is not randomly distributed. Its structure has a specific statistical signature, and the Planck satellite's measurements of the CMB match the predictions of inflationary theory with a precision that continues to astonish the physicists who work on it. There is one more piece of this picture that needs to be placed carefully. Somewhere in the very early universe, within the first second, during the quark-gluon plasma phase, something happened that should not have happened, and the fact that it did is why you exist. When matter and antimatter are created from energy, they are always created in equal quantities. A particle and its antimatter counterpart, identical in every way except for opposite charge. When they meet, they annihilate each other, converting back to pure energy. If the early universe had produced exactly equal amounts of matter and antimatter, everything would have annihilated everything. The result would be a universe of pure radiation with no matter in it at all. No atoms, no stars, no planets, no anything. But there is matter in the universe. You are made of it. The reason is a tiny asymmetry, an imbalance of roughly 1 part in a billion, in the amount of matter versus antimatter produced in the Big Bang. For every billion antimatter particles, there were 1,000,000,001 matter particles. When the mutual annihilation was complete, that 1 in a billion surplus was what remained. Everything you can see, everything that has ever existed in physical form, every galaxy in the observable universe is the residue of that tiny imbalance. We are, in the most literal sense, the leftovers. The physics that cause this asymmetry, a phenomenon called baryon asymmetry or CP violation, is still not fully understood. We can measure the asymmetry, we can confirm it exists. We cannot yet fully explain where it came from, which means that the reason for your existence is currently an open question in fundamental physics. Cosmology is like that. It answers enormous questions and in doing so, immediately produces bigger ones. Here is where honesty requires us to slow down, because everything described in the previous section, the quark-gluon plasma, the recombination epoch, the inflationary expansion, the fossil radiation ringing across the sky, is presented with a confidence that is, in several important respects, not entirely earned. The Big Bang framework is the best model we have. It is supported by multiple independent lines of evidence. But the difference between our best model and a complete and verified description of reality is a gap that cosmologists are acutely aware of, even when public science communication tends to paper over it. Start with the most fundamental problem, the moment of the Big Bang itself, the singularity. The point of origin is not something physics can currently describe. At the extreme densities and temperatures of the very beginning, two of the most successful theories in scientific history, general relativity and quantum mechanics, produce results that are mutually incompatible. General relativity describes gravity and the large-scale structure of space-time with extraordinary precision. Quantum mechanics describes the behavior of matter and energy at the smallest scales with equally extraordinary precision. But when you try to apply both simultaneously, as you must to describe a universe compressed into a subatomic volume, the mathematics produces infinities, nonsensical results that indicate not that the universe is actually infinite in those quantities, but that the theories are being pushed beyond the boundaries of their validity. A theory of quantum gravity, which would reconcile the two frameworks and allow us to describe the universe at the Planck scale, the smallest meaningful unit of length, roughly 10 to the minus 35 meters, does not yet exist. String theory is a candidate. Loop quantum gravity is another. Neither has been experimentally confirmed. Until we have a working theory of quantum gravity, the first 10 to the minus 43 seconds of the universe's existence, the Planck epoch, is simply beyond the reach of current physics. We cannot see past that wall. We do not know what we are missing behind it. Inflation presents its own set of problems. Alan Guth's original inflationary model solved real observational puzzles: the horizon problem, the flatness problem, the absence of magnetic monopoles that earlier models predicted should be everywhere but aren't. That is genuinely impressive. But the inflationary framework has grown into something so flexible that some physicists have begun to question whether it is truly scientific in the Popperian sense. That is, whether it makes specific predictions that could, in principle, be falsified by observation. There are now hundreds of different inflationary models, with different proposed mechanisms for what caused inflation and what ended it. Many of them make overlapping predictions. Some make contradictory ones. When a theory can be adjusted to accommodate almost any observational result, it starts to look less like an explanation and more like a vocabulary, a set of words that can be arranged to describe anything after the fact. The most direct way to test inflation would be to detect the gravitational waves it should have produced. The inflation was violent enough that it should have generated a background of primordial gravitational waves, ripples in space-time that would leave a specific imprint on the polarization of the CMB. These are called B-mode polarization signals, and their detection would constitute strong evidence for inflation. In 2014, a telescope at the South Pole called BICEP-2 announced exactly this detection in what briefly appeared to be one of the most significant scientific announcements of the decade. The announcement was premature. When the Planck satellite's data on galactic dust was properly accounted for, the signal that BICEP-2 had detected was consistent with contamination from dust within our own galaxy rather than primordial gravitational waves. The detection evaporated. The search continues with BICEP-3 and the Keck array, and the James Webb Space Telescope is adding new observational capabilities. But as of now, the gravitational wave signature of inflation has not been convincingly detected. Then there is the problem of dark matter and dark energy. And if those two terms make you feel like the universe is less well understood than the textbooks imply, that instinct is correct. Ordinary matter, the stuff you are made of, the stuff stars are made of, and every atom of hydrogen and carbon and oxygen in the observable universe, accounts for approximately 5% of the total energy content of the cosmos. 5%. The remaining 95% consists of dark matter, which we can detect only through its gravitational effects and have never directly observed, and dark energy, which is driving the accelerating expansion of the universe and which we understand so poorly that we have given it a name, is arguably the most accurate description of our current knowledge about it. The standard model of cosmology, called lambda CDM, incorporates both dark matter and dark energy as parameters. It fits the observational data remarkably well, but a model that fits the data is not the same as a model that explains what is actually happening physically. We do not know what dark matter is. We do not know what dark energy is. We are describing the universe with two components that together constitute 95% of everything, and we cannot tell you what either of them actually consists of. There is also a more recent and increasingly awkward problem called the Hubble tension. The Hubble constant, the rate at which the universe is currently expanding, can be measured in two independent ways. You can measure it from the CMB, using the early universe as your reference point, or you can measure it from observations of supernovae and Cepheid variable stars in the local universe using the present day as your reference. Both methods are precise. Both are well established. They disagree. The discrepancy is now significant enough that statisticians consider it unlikely to be a measurement error. Something is wrong, either with our understanding of the early universe or our understanding of the late universe, or possibly both. It may indicate new physics that our current models do not contain. It may be pointing at something beyond the Big Bang framework as currently formulated. Nobody yet knows. It is one of the most actively debated problems in cosmology right now, and its resolution, whatever it turns out to be, will almost certainly require revision of something we currently consider settled. Science at the frontier is not a clean room. It is a place where the instruments are imperfect. The theories are provisional, and the confidence that comes through in summary articles and documentary narrations is always a simplification of a messier and more uncertain reality. That is not a weakness. That is exactly how it should work. The uncertainty is the honest part. And in this field, the honest parts happen to be the most interesting ones. Let's travel through time. Not metaphorically. Let's actually follow the universe from its first coherent moments to the present, stopping at the places where the story becomes unexpected, where the science reveals something that the tidy summary version always leaves out. Because the history of the cosmos is not a smooth progression from chaos to order. It is stranger than that. It is, in several places, a story about things that should not have happened, happening anyway. Begin at 3 minutes after the Big Bang. The quark-gluon plasma has cooled and hadronized into protons and neutrons. The universe is now a dense, furiously hot sea of these particles, along with electrons and the nearly massless, almost ghostly particles called neutrinos. At this temperature, roughly 1 billion degrees, something remarkable begins. Protons and neutrons start fusing together, not in stars, which don't exist yet, just in the ambient heat of the universe itself. This process, called Big Bang nucleosynthesis, lasted for only about 17 minutes. 17 minutes out of 13.8 billion years, during which the temperature and density conditions were exactly right for nuclear fusion to occur in the open universe. When those 17 minutes were over, the universe had produced its first atomic nuclei, predominantly hydrogen, about 25% helium by mass, and trace amounts of lithium and deuterium. Those ratios are not arbitrary, they are predictions. The Big Bang model predicts specific abundances for these light elements, and when astronomers measure the oldest, most chemically pristine regions of the universe, ancient gas clouds that have not been contaminated by later stellar processes, they find helium at almost exactly 25%. The match is one of the most precise confirmations of the Big Bang model that exists. The universe spent 17 minutes cooking its first chemistry, and we can still read the recipe. Now comes the long wait. After nucleosynthesis, after recombination at 380,000 years, after the CMB was released and the universe became transparent, there is a period that cosmologists call, with a bluntness that suits it, the Dark Ages. No stars yet, no galaxies, just hydrogen and helium gas, slowly cooling, slowly thinning, drifting in the dark. The universe was not empty during this period. It was filled with matter, but it was lightless. There was nothing to generate photons. The CMB radiation was there, cooling and redshifting as the universe expanded, but no new light was being produced. For perhaps 150 to 200 million years after the Big Bang, the universe was dark in a way it has never been since. If you could somehow have been present in that void, which again you could not, you would have experienced a darkness more absolute than anything that exists today, anywhere in the cosmos. But in the dark, gravity was working. Those tiny density fluctuations seeded by inflation were growing. Regions slightly denser than average were pulling in more matter from their surroundings. Very slowly, over millions of years, clouds of hydrogen began to collapse under their own gravity. As they collapsed, they heated. The interior of a collapsing gas cloud gets hotter as the infalling gas compresses, in the same way that the air in a bicycle pump heats up when you compress it quickly. At a certain threshold, when the interior temperature of a collapsing hydrogen cloud reached about 10 million degrees, the pressure became high enough and the temperature high enough to ignite nuclear fusion. Hydrogen nuclei began fusing into helium. Energy was released, and the first star in the universe switched on. We do not know exactly when this happened. Current estimates place the formation of the first stars somewhere between 100 and 200 million years after the Big Bang. We have never directly observed a population 3 star, as these hypothetical first stars are called, because they would have been so massive, burning so ferociously, that they would have lived for only a few million years before exhausting their fuel and exploding. But their existence is inferred from the physics and from the chemistry of what came after, because those first stars contained only hydrogen and helium. There was no carbon, no oxygen, no iron, no silicon. None of the heavier elements that make up planets and people. The periodic table, as we know it, did not yet exist. The only atoms in the universe were the ones that came out of the first 17 minutes. And here is one of those small, illuminating details that changes the way you think about everything else. Every atom in your body heavier than hydrogen and helium was manufactured inside a star. The carbon in your cells, the oxygen in your lungs, the iron in your blood, the calcium in your bones, none of it existed at the Big Bang. All of it was forged in stellar interiors through billions of years of nuclear fusion and scattered into space when those stars died. You are not made of primordial material. You are made of stellar exhaust. Carl Sagan said we are star stuff, and it is one of the most frequently quoted lines in popular science, which has the unfortunate effect of making it feel like a pleasantry. It is not a pleasantry. It is a precise description of your chemical origin. The iron in your blood was literally cooked inside a star that exploded before our solar system formed. The first stars, those population 3 giants, would have lived briefly and died violently, seeding the early universe with the first traces of heavy elements. Over the following hundreds of millions of years, successive generations of stars formed from increasingly enriched gas clouds, in each generation incorporating the ashes of the previous one, each generation capable of producing more complex chemistry than the last. It was during this period, roughly 1 to 3 billion years after the Big Bang, that galaxies were assembling in earnest. The density fluctuations left by inflation were collapsing on larger and larger scales. Galaxies were not formed one at a time, like beads being threaded. They formed in the context of vast filaments and sheets of dark matter, the cosmic web, which provided the gravitational scaffolding along which ordinary matter flowed and pooled. Galaxies formed preferentially at the nodes of this web, where filaments intersected, drawn together by dark matter halos that outweighed the visible matter they contained by roughly 5 to 1. The universe at 1 billion years old would have been unrecognizable. Galaxies were smaller, more irregular, and far more active than they are today. At the center of almost every large galaxy, including our own, sits a supermassive black hole, objects with masses ranging from millions to billions of times the mass of the Sun. In the early universe, when gas was plentiful and galaxies were still assembling, these black holes were actively accreting matter at prodigious rates, releasing enormous amounts of energy as they did so. We observe this as quasars, quasi-stellar objects that outshine their entire host galaxies by factors of hundreds, visible across billions of light years. Some quasars were producing as much energy as 1 trillion suns from a region no larger than our solar system. They were the brightest objects in the universe, powered by matter falling into black holes at the centers of young galaxies. When astronomers look at the most distant objects in the sky, they are looking back in time. The light has taken so long to reach us that we are seeing those objects as they were billions of years ago. The most distant quasars we have detected existed when the universe was less than 1 billion years old. We are looking at the universe in its violent adolescence. This is the thing about looking at the sky that takes some getting used to. It is not a view of the present. It is a layered archive of the past, with distance corresponding directly to time. The moon as we see it is about 1.3 seconds old. That is how long its light took to reach us. The sun is 8 minutes old. The nearest star, Proxima Centauri, appears to us as it was 4 years ago. The Andromeda Galaxy, the nearest large galaxy to our own, is visible to the naked eye on a clear, dark night. But the light entering your eye left Andromeda approximately 2.5 million years ago, when our ancestors were still making stone tools on the African savanna. The most distant galaxies detected by the James Webb Space Telescope were observed as they existed more than 13 billion years ago, within the first few hundred million years of the universe's life. When the Webb telescope released its first deep field image in 2022, a patch of sky smaller than a grain of sand held at arm's length, filled with thousands of galaxies. It was showing us the universe as it existed at multiple different points in its history simultaneously, a cross-section of cosmic time stacked in a single photograph. The James Webb Space Telescope has itself been one of the more disorienting recent chapters in this story. Launched on Christmas Day 2021 and operational by mid-2022, Webb was designed in part to observe the first galaxies, to see further back in time than any previous instrument and test our models of early galaxy formation. What it found, almost immediately, was unexpected. Webb detected galaxies that appeared to have already been massive, already well developed, at redshifts corresponding to the first 400 to 700 million years after the Big Bang. These galaxies were larger and more structurally mature than the standard model of galaxy formation predicted should have been possible so early. Some cosmologists initially described them as impossibly large. That word was perhaps premature, and the community has been working through the implications carefully. But the genuine surprise in those first Webb results was not manufactured. Several theoretical models of early galaxy formation required revision. The early universe appears to have been more efficient at building galaxies than we expected. Why exactly remains under active investigation. Meanwhile, our own galaxy had its own story to tell, and it is one that connects the cosmic to the personal in a way that is worth pausing on. The Milky Way formed roughly 13.6 billion years ago, almost as old as the universe itself. Our solar system, though, did not form until about 4.6 billion years ago, meaning the Milky Way existed for more than 9 billion years before the Sun switched on. During that 9 billion years, multiple generations of stars had formed, lived, and died within our galaxy, each generation enriching the interstellar medium with heavier elements. By the time the cloud of gas and dust that would become our solar system began to collapse, it was already laced with carbon, oxygen, nitrogen, silicon, iron, and every other element on the periodic table above helium. The chemistry required to build a rocky planet was available. The chemistry required to build amino acids was available. The chemistry of life was possible because enough stars had already lived and died to produce it. There is a scientist whose work sits at the intersection of all of this, not a cosmologist, but a geochemist named Claire Patterson, who spent most of the 1950s painstakingly measuring lead isotope ratios in ancient meteorites to determine the age of the Earth. The work required him to develop entirely new contamination control techniques because even the microscopic traces of lead in ordinary laboratory air would corrupt his samples. He worked in what was effectively one of the first clean rooms in science, obsessive about purity in a way his colleagues initially found eccentric. In 1956, Patterson published an age for the Earth of 4.55 billion years, a figure that has been refined slightly but stands essentially confirmed to this day. It placed Earth's formation in context, not at the beginning of the universe, not near its end, but at a specific point in a long cosmic history during which the necessary chemistry had time to accumulate. The universe needed to be old enough, and enough stars needed to have died before a planet like Earth was even chemically possible. We exist not just at a specific point in space, but at a specific point in cosmic chemistry. Earlier than 13 billion years ago, the ingredients weren't ready, which raises the question that the entire journey through cosmic history has been quietly building toward. If the universe began 13.8 billion years ago, if it went through this precise sequence of events, if the fundamental constants of physics had values that allowed matter to form, and stars to ignite and heavy elements to be forged, and planets to coalesce, and chemistry to occur, then the natural and unavoidable question is whether any of this was inevitable. Whether a different universe with slightly different physical constants would have produced anything at all. Because when physicists actually run the numbers on this, the answer is genuinely startling, and it is the answer that takes us to the most contested and philosophically loaded territory in all of modern cosmology. Here is the number that changes everything. The physicists call it fine-tuning, and once you understand what it actually means, the universe stops feeling like a backdrop and starts feeling like an argument. Take the cosmological constant, the value that describes the energy density of empty space, the quantity Einstein invented and abandoned, the thing we now associate with dark energy and the accelerating expansion of the universe. When physicists calculate what the cosmological constant should be based on quantum field theory, our best description of matter and energy at the smallest scales, they get a number. When they measure what it actually is, from observations of the universe's expansion, they get a different number. The discrepancy between the theoretical prediction and the observed value is not small. It is not a rounding error. The theoretical prediction is larger than the observed value by a factor of 10 to the power of 120. That is a 1 followed by 120 zeros. This is the largest discrepancy between a theoretical prediction and an experimental measurement in the entire history of science. Physicists call it the worst prediction in physics. Some call it the vacuum catastrophe. And what it means, in plain language, is this. Something is cancelling out almost all of the vacuum energy that quantum field theory says should exist, leaving only a tiny residual that drives the gentle acceleration we observe. We have no idea what is doing the cancelling. We have no theory that explains it. We have a number that matches observation, and no understanding of why that number is what it is. But the fine-tuning problem goes further than the cosmological constant. Run the thought experiment properly. Take the fundamental constants of physics, the strength of gravity, the strength of electromagnetism, the masses of the electron and the quarks, the ratio of the electromagnetic force to the gravitational force, and ask what happens if you change them. Not by large amounts, by tiny amounts. Change the strength of the strong nuclear force, which holds atomic nuclei together, by 2%, and carbon cannot form in stars. No carbon means no organic chemistry, and change the ratio of the electromagnetic force to gravity by a small factor, and stars either burn out in millions of years rather than billions, or never ignite at all. Change the mass of the electron slightly, and atoms as we know them cannot exist. The universe appears to be balanced on a knife edge of physical constants, each one calibrated to a precision that allows complexity, chemistry, and ultimately life to exist. Tilt any one of them by a small amount, and you get a universe of hydrogen gas that never forms stars, or a universe that collapses back on itself in seconds, or a universe that expands so fast matter never has time to clump together at all. Now here is the pivot. Here is the thing that the clean, confident narrative of Big Bang cosmology tends not to dwell on. We have an extremely good description of what happened. We have almost no understanding of why it happened the way it did. Think of it this way. Imagine you walk into a room and find a safe. The safe has 100 dials, each with 1,000,000 possible settings. You try the combination and it opens. The reasonable question is not whether the safe is open. You can see that it is. The reasonable question is who set the combination and why those settings rather than any of the trillion other possible combinations that would have left it locked. Cosmology has spent a century confirming that the safe is open. The question of the combination remains essentially untouched. The three responses to this situation currently on the table in physics are each, in their own way, extraordinary. The first is the multiverse. The proposal, arising naturally from inflationary theory, that our universe is one of an effectively infinite number of universes, each with different physical constants, and we find ourselves in one compatible with life simply because the others don't produce observers to notice them. This is called the anthropic principle, and it is either the most elegant resolution to the fine-tuning problem or the most elegant way of not answering it, depending on your disposition. A theory that explains everything by proposing infinite unobservable universes is, some physicists argue, not really a scientific theory at all. It is a philosophical position wearing mathematics as a disguise. The second response is that we are missing physics, that there is a deeper theory, not yet discovered, from which the current constants emerge necessarily, and that in the final theory there will be no free parameters, no arbitrary dials, just one inevitable set of numbers that could not have been otherwise. This is what Einstein believed. It is what drove his search for a unified field theory in the last decades of his life. It remains the hope of many theoretical physicists today. It may be true. We have no evidence yet that it is. The third response is the one that science cannot officially endorse, but also cannot entirely dismiss, which is why it tends to be discussed in footnotes and late-night conference conversations rather than journal abstracts. The third response is that the fine-tuning is real, the multiverse is untestable, the deeper theory doesn't exist, and the constants are what they are because the universe was designed to produce what it produces. This is not technically a scientific statement. It is not falsifiable. But neither is the multiverse, and the multiverse gets discussed at physics conferences without anyone leaving the room. The honest position, the one that the data actually supports without philosophical overlay, is that we have a universe with specific physical constants that permit complexity and life. We do not know why those constants have the values they do, and every proposed explanation currently on the table either relies on unobservable entities, undiscovered physics, or something that sounds a great deal like the oldest answer in human history. The Bible said in the beginning, science confirmed there was one. The question of what that means, of whether a beginning implies a beginner, of whether fine-tuning implies a tuner, is not a question that physics has answered. It is not even clear that physics can answer it. What science has done, with 100 years of extraordinary effort, is sharpen the question to a precision that makes it impossible to dismiss. We no longer have the comfortable option of an eternal, self-explaining universe. We have a universe with a birth certificate, a specific age, a precise set of physical laws, and a beginning that our best mathematics cannot see past. The question that ancient text was asking turns out to be exactly the right question. Whether the answer it proposed is also correct is, at present, above science's pay grade. Consider what we have actually accomplished. In roughly 100 years, less time than it takes light to travel a few hundred light years, a trivial distance on any cosmic map, human beings went from not knowing the universe had a beginning to measuring the temperature of its first light to within a fraction of a degree. We went from debating whether the Milky Way was the whole of existence to cataloguing 2 trillion galaxies. We went from Einstein inserting a fudge factor into his equations because an eternal universe felt safer, to launching a telescope the size of a tennis court to the second Lagrange point, 1,000,000 miles from Earth, to photograph galaxies that formed within the first few 100 million years of time. The James Webb Space Telescope, that gold-segmented mirror unfolding in the cold dark between Earth and Sun, is arguably the most complex object our species has ever built. It was 25 years in development, involved the coordinated effort of thousands of scientists and engineers across multiple continents, cost $10 billion, and had to unfold correctly through 344 separate deployment steps after launch, every one of which had to succeed, or the entire mission would fail. It succeeded, all 344, and it is now sending back images of a universe in its infancy that are rewriting our models of how galaxies form. That achievement sits alongside others that deserve to be named in the same breath. The Apollo program put 12 human beings on the surface of another world using computers less powerful than a modern wristwatch. The Voyager probes, launched in 1977, are now in interstellar space, still transmitting, the farthest human-made objects in existence, coasting through the void beyond our solar system on a journey that will bring them near another star in roughly 40,000 years. The Event Horizon Telescope, not a single instrument, but a planet-spanning array of radio telescopes coordinated to act as one, produced the first direct image of a black hole's shadow in 2019, confirming a prediction of general relativity that Einstein himself doubted we would ever be able to test. LIGO detected gravitational waves in 2015, ripples in space-time from 2 black holes merging over 1 billion light-years away, a signal so faint that the detectors had to measure a displacement smaller than 1,000th the diameter of a proton. These are not small achievements. These are among the most extraordinary things any civilization on any planet has ever done, as far as we know. And yet, against the backdrop of what remains unknown, they are the first few sentences of a very long book. We do not know what dark matter is. We have been searching for it directly, either with increasingly sensitive detectors buried deep underground to shield them from cosmic ray interference, for decades. It has not been found. We do not know what dark energy is, beyond the observational fact that it exists and is accelerating the expansion of the universe. We do not know what happened before the Big Bang, or whether that question even has a meaningful answer. We do not know whether inflation occurred, or what caused it, or what ended it. We do not know whether our universe is one of many or the only one. We do not know why the physical constants have the values they do. We do not know why there is something rather than nothing. These are not peripheral questions. They are the central questions, and they remain open. What would it mean to answer them? A confirmed theory of quantum gravity would not just resolve a tension between 2 frameworks. It would give us access, for the first time, to a physical description of the moment of creation itself. A confirmed detection of primordial gravitational waves would tell us not just that inflation happened, but how violent it was, and perhaps what caused it. A direct detection of dark matter would reveal that 27% of the universe's total content, currently invisible to every instrument we have, has a physical identity we can study and understand. Any one of these discoveries would rank among the greatest intellectual achievements in human history. All of them remain within the realm of possibility in the coming decades, given sufficient resources, sufficient ingenuity, and sufficient willingness to sit with hard questions rather than retreat to comfortable answers. There is something quietly remarkable about the fact that the question science has been working toward for a century, whether the universe had a beginning, was already written down, in plain language, thousands of years before we had the tools to investigate it, not as a scientific claim, as a statement of faith. And the science, when it finally arrived with its telescopes and its mathematics and its cold, careful measurements, looked at what the ancient text had said and found, to no one's particular comfort, that it was not wrong. The universe did begin. Time itself had a starting point. Something came from nothing, or before nothing, or instead of nothing. And the grammar of that sentence breaks down because our language, like our physics, was not built to reach that far back. We are a species that looks up. We always have been. From the first human who noticed that the stars moved in patterns, to Lemaitre doing field equations in a Belgian monastery, to the engineers who held their breath through 344 deployment steps on Christmas morning, 2021, we have never stopped trying to see further than we can see, to know more than we currently know, to push the boundary of the answerable just one question further into the dark. We do not know what is on the other side of the beginning. But the fact that we are asking, with this much precision, with this much humility, with instruments of this extraordinary delicacy, that in itself, it is one of the more astonishing things about the universe. It produced something capable of wondering about it. Whether that means anything is perhaps the oldest question of all.